moment of the Big Bang spat out space and time and the infinity stones. They were complete in their structure even at the moment of the Big Bang. The rest of the universe was this hobgoblin of particles and shit like that. But no, the infinity stones were just solid stone even at the birth of the universe. That's quite amazing, actually. Other questions? I don't know anything about the infinity stones, but I'm guessing.
So the second question, my final dumb question of the semester and my college career. Which could you more feasibly fight? Not kill, because they would kill you, but feasibly fight a pterodactyl with bodybuilder arms or a megalodon with bodybuilder?
Or a what?
Megalodon.
I don't know what a megalodon is.
Do you really not know what a megalodon is? Guys, this is happening separate with
Just say it like a brachiosaurus with a weightlifter's tail.
It's a big ass shark.
Oh, it's a big ass shark. Oh no, I would take on the pterodactyl because I can't breathe underwater.
I mean, yeah, but it like just pick you up and
I'd take the pterodactyl any day. Yep, I'd take the pterodactyl. No problem with it. No problem with it. Any other questions? Okay, we have got a ton to get through, and I'm just going to stop when it's time to stop. I'm not going to keep you guys here super late. I could talk forever. I took an entire course in cosmology as a graduate student at CU, and it was funny how we just kind of sifted through this stuff so slowly, and now, you know, I'm going to do cosmology in 2 lectures for you. That makes no sense to me, but that's the way it is. All right. So let me get started by going back to the Big Bang, because we are thinking about those infinity stones. So let me remind you of where we are, or the Friedman equation. That's the equation. And by the way, this lecture is going to have a little bit of, you know, mathy stuff at the beginning, and then it's just going to turn into words at the end, okay? Because truthfully, going through all the calculations that are relevant for the things that I want to present to you is just too much. But I think I really want to present some of the outstanding problems facing cosmology to you. So we'll do that in words a little bit later on. But remember, the Hubble parameter is defined as the time derivative of the expansion of the universe, or the scale of the universe, which is this time-dependent function A. It's the time derivative over A itself. That's h, but we're squaring both because Friedman's equation involves these. And this can be written as 8 pi g over 3 times the energy density. I got to figure out how to make my mask stay up because it keeps coming down my nose. I so wanted to do a maskless lecture today. It's really irritating the crap out of me. But anyway. Okay, there we go. Loosen it up. All right. Good. All right, minus. And this was K with like little knobs on it. I'm just going to go back to normal K, but that's the K with little knobs on it that I ended up with in the last lecture. I just wanted to do that every time I write the letter K. Over A squared. This is the Friedman equation. And so we did some things with this. First of all, we realized that this is the sum over all possible energy density contributions, okay? But if we redefine the vacuum energy as just this thing, you know, with factors that make it have the same 8 pi g over 3 factor in front, we can actually simply write this as 8 pi g over 3 times the sum over I, rho I, where I equals matter, radiation, vacuum, or curvature. Okay, we're going to talk a little bit more about those different energy densities, so that's why I want to put that there. But very quickly to remind you, the energy density of matter in the universe evolves proportionally to 1 over A cubed, where again, A is basically the standard length of the universe. Radiation evolves as A to the 4th. Okay, this obviously matter, the evolution of matter is 1 over A cubed. This is a matter density, and obviously if the density increases, you know, that's a volume, A cubed, so that's why this density gets smaller as A gets bigger. This gets smaller because the volume is getting bigger, but also because of the redshift, okay? And that only affects one direction, the direction the particle's moving. It's redshifted along that direction, and so you get an extra factor of A. And then the vacuum is kind of weird. It's a constant. Okay? Now, let's take this and do something with it. And that something is going to be, let us, for a moment, guess that at some time, the universe is dominated by one of these energy densities. Okay? And by the way, curvature obviously goes as a to the minus 2. This is the curvature term, but we're just going to wrap it into the energy density contributions, but it obviously goes as a to the minus 2. Okay? So what we want to do is we want to say, okay, let's suppose that the universe is dominated by one of these forms of energy. So there's much more of one of these than the others. And then we can use just that evolution in the Friedman equation. Okay? And what we'll basically find is that h squared is 8 pi g over 3 times a to the minus n. Okay? Where the choice of n just depends on which energy density we're dominating things with. And now hopefully you realize this is a pretty simple differential equation because h is just a dot over a. And the right-hand side is proportional to a to the minus n. So we can just take this and solve for a as a function of t. And what we find is the following, and I wish I hadn't done that. I'll do it here. We find that, well, I'll write it, yeah, I'll write it here. A of t, in this case, is proportional to t to the 2/3. In this case, a of t is proportional to t to the 1/2. In this case, a of t is proportional to t, and in this case, strangely, a of t is proportional to e to the ht. Okay? Again, this is a really simple differential equation, you guys. I mean, I solve it in the notes, but I'm not going to lay out the solution. Now let's ask ourselves, folks, welcome, Josh, with his midterm solution to the midterm exam in math physics. No, bring it up to the front and show it. In graduate mathematical physics last semester. That's page 1, folks. Yeah. I'll fold it off to the edge, and you do the flippage.
See if I can get this up.
It's quite difficult.
It is difficult.
Okay, yeah. Anyway, so we've got the second part of that question, the third part, but it gets better. Because pipe cleaners are not the only way to go. You can also use crayons.
This one was, I think it was, what's it called? Chalk.
Oh, sorry, 12.
We'll just hold it like that.
Yeah.
How did you do this in 2 hours?
I did.
No, he didn't. It was a take-home midterm.
This one was my favorite though. The ransom note. And the macaroni art.
Yeah, there's macaroni, there's letters cut out from various sources, and a threat of physics. More, and
The pen.
the pen. Yeah. Oh my goodness. He'll let you read it later. All right, thanks, Josh. I appreciate you bringing that over. Just to let you know, please don't ever do that again. It's a one-time thing. It's awesome. Never again.
That's what makes it the best.
Yes,
It's only
it is.
those
It
ones.
is. Thank you so much. Okay, now, all right, so, sorry about that. So for early times, which of these energy density contributions would you expect to dominate? Hannah?
In the early times, if t is small.
Say it again?
Like, what do you mean by the early times?
When A is small.
When a is small.
So A is at its smallest value, so if you have a fraction with A in the denominator to a power, which most of these are, which one of those dominates if A just gets smaller and smaller and smaller? The matter, the radiation, the vacuum, or the curvature? This is
Oh, I was looking, okay.
Yeah, don't look here, look here. Sorry,
Okay.
look here.
The A to the zero, the vacuum.
Well, this one is actually undetermined. This is constant. This doesn't evolve at all.
Okay. Then
But what do each of these go to when A goes to 0?
and then
Which one goes faster?
the radiation.
Yeah, it's the radiation. So at the early times in the universe, we expect the universe's energy density was dominated by radiation. What about at late times? Drew, and yes, I do have all the award winners cards on top. Drew, at late times, which one do you think wins? Vacuum, okay? And at some point in between early times and late times, we might have a matter or a curvature-dominated contribution to the energy density of the universe, okay? And we're going to talk about the contributions to our current universe that each of these provide, and we're going to talk about that in a bit. But here's the most important observation. The two of you just told me that radiation probably dominates in the early universe, and vacuum is important for the late universe, and this is least important for the early universe. If you think about it, early in the universe, you've got stuff. And there might be some vacuum energy there, but you've got so much stuff that the stuff contributes more energy. As everything spreads out, the distribution of stuff gets smaller and smaller and smaller, but the vacuum energy doesn't decrease at all. So eventually the energy density associated with the stuff will go to 0 if the universe expands large enough, but that vacuum energy is going to be the same. Let's go hang out. I'm the same! So if I didn't have my mask on, you'd laugh. Anyway, so I would argue that at the beginning or early in the universe, this is irrelevant. Okay? Now that's important because of these. These are telling us how the size of the universe depends on time. What does this predict?
Size of the universe is 0 when time is 0.
Which is what? What do we call that?
Singularity.
But it has a special name.
Oh, the Big Bang.
The Big Bang, yeah. Sorry. This is our prediction of the Big Bang. Okay? And the infinity stones, or that's what they're called, yeah. Okay? So there is one of our first, I mean, look, we've been kind of talking about early in the universe things being smaller, but you have to be careful, like, how did we figure that out? I just showed you how we figured it out. Of course, you already know, you're so well versed in this, you might be like, yeah, you proved that to me. I know the universe is getting bigger. I knew it was a Big Bang. No, we have to prove this because we didn't see the Big Bang. But here it is. Okay, based on this argument that we can largely ignore vacuum contributions early in the history of the universe, the length scale of the universe A is going to 0 as t goes to 0. Okay? It means our universe was infinitesimal. Okay? That's the Big Bang. All right. Now, let me say some and by the way, this is a singularity, as you pointed out, but it doesn't violate the condition that says every singularity that results from collapse must be covered by an event horizon, because this one is not the result of collapse. Okay? So this is actually an example of a naked singularity. All right, so now, cosmology, so today's lecture, this was just kind of the end of last lecture, but today's lecture is really going to take this Friedman equation and all these definitions I've given you so far and answer the question, okay, what about our universe? Okay, the Friedman equation is an equation that you can solve, you know, picking different combinations of this stuff, and saying, what's this universe or what's that universe, you know, but we want to know what is our universe. How do we take measurements? How do we figure out the actual values of these? How do we figure out the value of H or rho or A or K? Okay? Now, first and foremost, this might be obvious, but I'm going to say it. Cosmology is an observational science versus an experimental one. If you think about it, most of physics and most of science is based on the notion of an experiment. You create something, you watch it go, and then you record the results. Then you repeat it, and you repeat it again, and then you have these people do it and repeat it. And that's how you grow confident in the end that your understanding of what's going on is real. Okay? Can we do that with cosmology? No. The universe began once. It's still evolving. That's it. There's no experiment to be done. Okay? The other thing, and so you observe, and you're just trying to make sense of the observations. Go for it.
Well, aren't there like ongoing experiments with like stuff like looking at the cosmic background radiation?
Say again?
The cosmic background radiation?
What about it?
Oh, just like, well, I guess, yeah. It's
Observing it or doing experiments with it?
Yeah, I guess it's.
Yes, everything is observational. When you do general relativity, it's hard to do a general relativity experiment, period. Because if you think about it, you know, to see the effects of general relativity, you need things the size of planets and stars. We can't manipulate those. We can send things into orbit and demonstrate that the calculations based on they follow the shortest path or the longest path, okay, they follow geodesic trajectories. We can test that part through experiment, okay, doing GPS corrections and so forth, but we can't actually create something and then measure the curvature of space-time that it induces, because you got to have something so big that the effects are actually measurable, okay? So a lot of this is just observational science, all right? Now, yeah, and obviously we can't do repeats, which is actually an important part of physics, that you be able to repeat an experiment, because no one trusts a one-hit wonder in physics. Okay, now there are so one of the sort of key ingredients in measuring things in cosmology is based on our understanding of astrophysics. Okay. So in order to go through, I mean, I'm not going to teach you astrophysics by any stretch of the imagination, but if you wonder what is astrophysics, well, astrophysics is essentially trying to understand the structure of stars. Now this is an example of where you will require the use of general relativity because they're so big. To understand their structure, you'll need general relativity. Obviously they curve the environment around them, but they're also curved inside, okay? But that's not the only force on the story. What other force is important?
Fusion?
Well, at least nuclear physics, at least the strong interactions, the weak interactions, and maybe electromagnetism in a certain degree, okay? So astrophysics goes way beyond general relativity. That's why we do not have time to cover this class, okay? It's a hybrid of general relativity and all of the other forces, essentially. It has been well thought out. Okay, again, it's an observational science, more or less. Okay, we can't create stars in the lab. We do. So goes the lab and Earth. But anyway, it's an observational science. But what it has produced for us are these things called standard candles. Okay. That is, we have such a good understanding of astrophysics, and if that's a star and it's got this size or it's got this spectrum, then we know this and that and the other about it, okay? And standard candles are important because when we look out in the universe, it turns out that measuring things gets really, really hard unless you know a lot about the thing that you're measuring. And it turns out the most easy things to see in space are stars, so that's why so much effort was poured into this. Okay? So we are going to refer to standard candles. And it's funny because their luminosity, their size, their emission spectrum, etc., these are all different things that we can measure from a standard candle. And then based on how the signal received is different than the signal we expect, is a statement or evidence about the geometry between the standard candle and us. Okay, so we can model, okay, if I were looking at it through flat space, then I should see this, but then when I look at it, I see something different, and that's telling me about the geometry. And of course, we can't do this with a single standard candle. We use all of the standard candles. We look at them all because they're ones at different distances, different sizes. We just do a survey over the entire sky in order to draw any useful information about what's going on. Okay, so if we want to talk about standard candles, we might imagine that if a standard candle had an emission spectrum, okay, so this is a discrete spectrum of emission from the standard candle, and maybe it moves from the UV range to the infrared range. Okay? Then when one looks at one, now this is based on the model of what it is. This is not what we see. This is based on I know that that's, a star of this size and it's made of this stuff, therefore I predict its emission spectrum should look like this. And then when we actually look at it, we tend to find that that emission spectrum is shifted. Okay? And what we can do is we can relate the size of this shift in the emission spectrum to, so we can talk about the observed frequency versus the emitted frequency of any one of these bars. We can immediately relate that to the ratio of the scale of the universe at the time of emission versus the scale of the universe at the time of observation. Remember, everything we look at in space, we're seeing as it was in the past. And this is where it gets crazy, right? If you look at that, you're looking at it 8 billion years ago. But if you look at that, you only look at it 7 billion years ago. And if you look at that, you look at it 15 minutes ago. So you can imagine how organizing things really sucks in general relativity and cosmology. Because you have to take into account, not just how big something is, you've got to take into account how far it is, and that correlates to its age. And this is based on you knowing the geometry that you're trying to calculate. That's weird. Okay? So you got to find different approaches to find the final answers about the geometry. Now, we can take this and we can define what's called the scale factor. And the scale factor is essentially lambda naught, the wavelength at the time of observation, minus the wavelength at the time of emission, divided by the wavelength at the time of emission. And you can very easily prove that that's A naught over A E minus 1, which leads us to the observation that the emitted scale factor is A naught over 1 plus Z. Okay? So we have that A naught, or A emitted, the time it's emitted, the scale factor is the time observed over 1 plus Z. Now here's the important observation. What is Z? Is Z positive, negative, or 0? Well, first of all, we see it shifted. But do we see a positive or a negative shift? It turns out we see a positive shift. So what did this just prove? Say it. It's expanding. Do you really think that we look out in space and go, yeah, he's moving away from me. Yeah, he's moving over there. He's moving over there. Yeah, no. We have to measure something. Okay? So what we do is we measure the frequency shift, and we note that since the frequency shift for all of these standard candles is positive, then AE is smaller than A naught. Okay? So we have an expanding universe. But we can do more than that. We can do a lot more than it turns out that we can relate the shift parameter z, the redshift, to the distance that we would like to know, or that we might measure, times the current value of the Hubble parameter. Okay, and I go through actually deriving this in the notes, but I'm not going to write it up. Okay? So again, this is the current Hubble parameter. The Hubble parameter evolves with the evolution of the universe, but this is the current value. That's what naught is going to mean throughout this lecture. D is the we'll talk about this in a moment. This is the distance from us to whatever thing we're looking at. And then Z is the shift for that particular object. The shift will be different for different objects. Okay? Because obviously, the objects, depending on their distance from us, are the light that we're seeing now is emitted at different times. So the scale factor is different. So the Z factor is going to be different. Okay? Now, we have D. Okay, so first of all, we can measure Z. We can measure the shift in the spectrum pretty straightforwardly. We would like to calculate H naught. We'd like to know the value of H naught. But we've got to talk a little bit about D first. Okay? In cosmology, it turns out that distance, it's not obvious. It's not straightforward. There's a gazillion different ways to define the distance in cosmology. So for example, we can define the coordinate distance. Okay, literally, this is if you want to put down a spherical polar coordinate system and ask how far out along the r-axis is that object. Okay, it's not particularly useful. It's not physical, but it is something that you would use in a calculation. Okay. Another, perhaps physical one is the equal time distance. That is, if we look at a standard candle and we say, how far away is it from me right now? That is a useful measure of distance. It's just useless because you can't see it. When you look out, everything you see is in the past. Does that make sense? Okay? I mean, it's a very useful idea. Like if I stand in this room and I say the distance between me and Josh is 4 meters, 3 meters, I don't know, 4 meters. Anyway, that's obviously a statement about that's the distance between us right now. Okay? That's a very useful concept in normal small-scale physics. Cosmological scales, this is kind of useless. We need to talk about what we can see. Okay? So the observed distance, this is more useful. Okay? I don't know why I keep writing the word distance. All of these are distances. I should just write observed, equal. Anyway, so, well, remember that the things we're looking at are giving off light, and we know how fast light travels. Okay? So there's a simple way to take the thing that you see, combine it with the speed of light, and figure out how old what you're seeing is. Okay? If there was a different mechanism of it communicating its presence to us, we would still have to know the velocity with which that signal was being sent to us. But fortunately, what we see when we look out is just the light coming at us, so we know how fast that moves. It gets more interesting, though, because we can sometimes find that angular separation is a good way to think about things. You want to look out and talk about, oh, there's this thing and that thing, and they're angularly separated by about this distance. Okay? You got to be careful. Are they the same distance from us? Okay? And then there is the angular size. And you might say, wait a minute, angular separation, angular size, what's the difference? Well, if you think about it, these two quantities behave very differently. If I have two objects, and the universe is expanding, then over time, their angular separation will grow larger. Okay? However, if I take into account that an object has a size, will it get bigger as the universe expands? What do you think? This is a big question. Does objects get bigger because space-time is expanding? Who says yes? Go ahead, say yes. Who says no? The no's have it. Actually, no is correct. Why? Why don't things get bigger? Space-time's expanding, the space between atoms is expanding, everything's expanding, damn it, let it expand. Why don't the size of things get bigger? Yes?
Because the scale on which we measure them also gets bigger?
So you're talking about co-moving coordinates?
Yes, those.
Yes, co-moving coordinates are the very useful coordinate system to use to work problems. However, things are actually moving apart. You're describing that with co-moving coordinates, but when you look out there and you look long enough, you'll see that it went from here to here. I actually moved my hands apart, you just can't tell. Small. Yes?
The expansion is very slow and other forces are existent.
So I think I heard what you said. It sounds correct. This is just two free bodies with no interaction, so their movement apart is due to the gravitational expansion of the universe. The extent of this is by no means only the gravitational expansion of the universe. Okay? This is the other forces binding things together. Okay? And those win. Because locally, they're always going to win compared to gravity. Okay? So even though space-time is expanding, if all of these particles, if it just happened to be a set of particles that were just floating near each other but totally not interacting, then yes, it would get bigger due to the expansion of the universe. But that's not what stars are, unfortunately. They're deeply interacting. That interaction wins, they stay the same size. Okay? So the reason I'm pointing this out is angular separation will evolve with time, but the angular sizes of objects will not evolve with time. Yes?
If the expansion is accelerating, doesn't that mean that there's at some point going to be a time where that wins out?
Sorry, say it again?
If the expansion of the universe
Well,
is
we'll talk about
accelerating-
that in a few minutes.
Oh, okay.
And I might or might not have enough to answer your question when we talk about it, but let me carry on before I start answering your crazy ass questions. Okay, so all of these can be related when we know the full geometry, okay? But a priori, first of all, they take different values, but at least once we completely and totally understand the geometry on which we're working, given this, we can figure out this, we can figure out this. There's no hassle, okay? But you have to remember, we're not at a point where we completely understand the geometry. We're trying to take data that we can use to figure out that geometry. That's where it becomes kind of a pain. Now there is another distance which actually proves to be quite useful, and this is known as the luminosity distance. And this basically says the luminosity is 4 pi times the luminosity distance squared times the measured flux. Okay? So this is known, this is one of the things that we know about a standard candle, because astrophysicists have done their calculations, figured out this should be putting out luminosity at this rate. Okay? Flux, of course, is what we measure. All right? And so therefore we can calculate the distance of anything if we know its luminosity and we measure the flux. Okay?
How do you measure the flux?
Say it again.
How do you measure the flux?
How do you measure the flux? Ooh. Oh man, are you talking to an experimentalist or a theorist? I did do a year in experiment. It was a year of learning to code C++, and I hated it, so I started doing theory instead. You probably have a better, more mature answer than I can give you. I could give you a undergraduate optics answer, but if I could remember it, but I don't quite remember. Is that okay, Sam? You can look it up though, I guarantee. You don't need me to answer it. All right?
Yeah.
Okay. At any rate, sorry. So, let me think. Oh yeah, here we go. So if we're working with low redshift observables, so if we're taking Z, we're taking things that have a relatively small redshift, then we are fairly confident that we can interchange the distance in this expression. This is derived from a separate set of expressions. We can interchange that distance with the luminosity distance of a standard candle, okay? The reason I say this is because we can obviously measure the frequency shift, or the redshift factor for a standard candle. Now we can figure out the distance for a standard candle. This leads us to a value for H naught. And in the end, H naught comes out to about 70 plus or minus 10 kilometers per second per megaparsec. Okay? Now, that's H. For large redshifts, things get more complicated. More of the geometry of the universe will play in. Okay, so we need to be much more comfortable in our knowledge of the geometry of the universe. But if we do this for small redshifts, these are close things. Okay, obviously the redshift gets bigger the further something is away. But if we're doing this for close things, then we can trust this approximation. There we have the current observable value, or the current calculational value of the Hubble parameter based on measurable quantities. But now we can play one of those interesting games. Kilometers per second per megaparsec. Well, that's a distance over a distance times time. The distance units could cancel if we put them in the right structure. But if you're ever doing sort of fundamental physics, which is to say you're studying a system where you're really only taking into account a single force, this is gravity, then when you actually have the value of a quantity, not in a quantity that defines the system, capital G is part of the definition of general relativity. It has a value, okay, so does C. They have values. But in terms of the model that you're working with, once you have a measured quantity on a sort of fundamental theory scale, you can, from that, through combinations with other constants which are in the theory, like the speed of light or capital G or whatever, you can pull out other values which are important. So for example, I could always cancel the distance units and have a 1 over seconds, and I can flip that over and get a time. The time comes out to be, which is really just 1 over H naught, 14.4 billion years. Okay? We can obviously take the speed of light and combine it with this to get a distance. And the distance ends up being 4.55 million parsecs. If you're curious, a parsec is 3 times 10 to the 13 kilometers. It's big. Now here's the deep observation. I've got a time scale and I've got a distance. What do you think those correspond to?
Size and the age of the universe.
The size and age of the universe. At the time, not now. Okay? So here's how we predict the size and age of the universe. Okay? And I mean, you know, and to verify this, I mean, this is kind of crazy, but to verify this, you know, you can look over there and you can use all the redshifts and the luminosity distances that you've calculated and figured out a value for H naught. And then you can instead look over there and do the same thing. You'll end up with the same value of H naught to this uncertainty. Okay? That's pretty big uncertainty. And it might be more accurate now than this. This is just from when I first taught this class, I wrote down that. Okay, it might be more accurate than that now. Okay? But in the end, you're confident about that number, and you get these two. You get the age and the size of the universe. It's pretty cool. Now, in order to complete this story, because now we've actually talked about what the current value of H is. By the way, this is a story which evolves with time. So this is going to be H as a function of T, where rho is a function of T, K is a function of T. We can always talk about its current state with H naught, rho naught, and K naught, okay? Because that's what we actually observe. Current state. So what we want to talk about now is what are these other quantities in here. And we're going to do a definition. So we're going to define omega I as 8 pi g over 3h squared times rho I, where this is just rho I over rho critical. Okay? Where rho critical is the energy density needed for k equals 0. What does k equals 0 describe, Matthew? Do you remember? We talked about it last time. We talked about if k is positive, negative, or 0, then our spatial geometry is either this, this, or this.
It's just depending on if it's closed, open, or flat.
Yes, and with k equals 0, which case is it?
It's flat.
It's flat, exactly, okay? So we're going to define this rho critical as the total energy density needed so that k equals 0, the universe is flat. Of course, that doesn't mean that we have to have that as our energy density. We're just defining a new scale, okay? Turns out they use the scale quite often. That's why I'm doing this. Okay, so if the sum over all of the contributions written in this form equals 1, then k equals 0. Okay? Because in order for this to be 1, the sum over all the rho i's has to equal rho critical. That makes this 1. But then you're saying that the energy density of the universe is rho critical. Okay? Does that make sense? Okay. All right. Now, of course, we make measurements at our current time, so we might say omega I 0 is 8 pi g over 3h naught squared times rho I 0. All right? These terms can be talking about the universe at any point in its history. However, this is the stuff we have observational data for. Okay? And now let's ask, what are the values of omega for the different contributions to the energy density? Remember, we have matter, we have radiation, we have vacuum, and we have curvature. So for, we'll do it here. So if we start with matter, what we do is we say, all right, let's look at a cluster and let's use gravitational effects to try and figure out what's the mass of that thing. So we're kind of using its size and an emotion, and we're just trying to sort of figure out, okay, this much mass has to be there. And then we can take the density with which we see clusters, and this will let us extrapolate to how much mass is in the universe. Okay? Because if you see a cluster here and you figure out its density, but it's the only cluster in the entire universe, then the density of matter is very small. But if you see one here, and one here, and one here, and one here, and it's sort of a uniform distribution, then that's going to diminish the intensity. Okay? So it turns out that this comes out to about 0.3 plus or minus 0.1. Okay? All of these numbers should be less than 1. Okay? Potentially greater than 0, but less than 1. All right? For the radiation, what we do is we use the cosmic microwave background radiation. Okay, that's a kind of an easy way to figure out how much radiation is left over in the universe, because we're at the current value of radiation. Okay? And the cosmic microwave background radiation is obviously the largest contributor. So we've measured the temperature of the cosmic microwave. It's about 2.73 degrees Kelvin. And then we can fit that to a thermal distribution, and what we find is that the radiation comes in at about 10 to the minus 4. Much smaller than the matter. Which is what we expected. Early in the universe, radiation might have dominated, but later on, matter would have overtaken it. Okay? Now, what about curvature? Well, to figure out curvature, what we do is we look at the separation between things, and we say, okay, we know the separation distance, but we would like to know, now, bear in mind, when I say we know the separation distance, I'm talking about from means other than simply looking at it. Okay? We have a different means of determining this distance. Okay. Now we look at it. What appears to us? Is it based on something like that? Is it based on something like this? Or perhaps it's based on something like this. I mean, what am I drawing? I'm drawing the trajectories of light that leave these things and come to our eyes. Here they kind of meld together. Here they just kind of move at 45, or they just move in straight lines, and here they kind of move at these. Well, what's the curvature of this space? The one in the middle. 0. This is the way light travels in flat space. What do you think the curvature of this space is? Think about it. If you're trying to draw geodesic paths on the surface of a two-sphere, they would look like this, right? You can't draw straight lines on a two-sphere. They always have to be bowed. So if you start at 2 points and draw 2 lines to a given point, they'll go like this. This is when the curvature is positive. This is when the curvature is negative. That make sense? So if we look at two things and we know how far apart they are, then we look at them and they're either going to be, well, how do we figure that out? Well, I mean, look, we project back. So what we think we're seeing is the light coming from a narrower scope, from the regular scope, or from a much larger scope. So if I know how far apart these two things actually are, and they actually appear closer, then we're dealing with this. If they do appear at the correct distance, then we're dealing with this, but if they appear to be more separated, then we're dealing with this. Well, now you can just ask me, which one is it? Because we've observed many things. No one's going to ask?
Which one is it?
It's k equals 0. Okay? So omega curvature, this is the curvature of the spatial part. Okay, and I should bear that in mind. K is the curvature of the spatial part of our geometry, not the space-time itself. That's 0. What about the vacuum? How in God's name are we going to figure out the energy density of the vacuum? Josh, how are we going to figure out the energy density of the vacuum?
My first thought was some quantum field theory messery.
Yep. That's where vacuum energies come from, all right.
Yeah.
You know where else they come from?
Event horizons.
Nope. You know what else they come from, folks? Arithmetic. We just said k is 0. If k is 0, the sum of omegas is 1. Well, we've got 10 to the minus 4 plus 0.3 plus 0. What's this? 0.7. Plus or minus 1. Okay? I know it seems a little bit circular, but that's the way you play out the argument. Okay? So, currently, the observations for the relative contributions to the energy density of our universe from matter, radiation, curvature, and vacuum are these. Okay? That is in addition to our current estimation of the Hubble parameter. That's it. That's all we need to solve this story. Okay? Now we're going to turn our heels and we're going to talk about some problems. And this is where it's going to get really wordy. I'm not going to go mathy on you. We will refer to some of the stuff that's on the board. But let's start out with the problem of dark matter, one which I guarantee you all heard of. So recall that omega m is around 0.3. Okay? That's a pretty reasonable, amount. Now you got to remember how we figured that out. We measured the rotational velocities of spiraling galaxies and used the gravitational model to figure out how much mass must be in there in order for it to be stable. Okay? We did not look at it and go, well, there's 1, 2, 3, 4, 5, 6, 7, 8, up to 8 gazillion stars in that thing, therefore. No, that's not what we did. Okay? We used the dynamics to figure out the mass energy contribution. Now you can simply ask us a more simple question. What if you just look out there and count what you see? That is, you want to know what is the luminous appearance of things. Well, if you look at it, what we see, you're basically seeing baryons. Okay, baryons are the neutrons, they're the protons. The electrons, those are so small they don't really contribute. Okay? The baryonic content of our universe is largely the largest contributor to the mass density. And if you add up everything that you see, you get a contribution way smaller. Okay? This, of course, means that there must be matter in the universe which is a large portion of the mass in the universe, but it is not mass that we can see, hence the name dark matter. Okay? Trying to figure out what this stuff is still an open challenge. We're making a lot of progress. There's a ton about it that's interesting. It's got to be non-luminous. It can't be putting off light because we can't see it. It's most likely not machos. You might immediately think, oh, maybe it's a black hole. A black hole doesn't put out that much, it doesn't put out any light. Well, it puts out a little bit, okay? But maybe you just got a gazillion black holes and that's the, nope, machos don't work. These are massive compact halo objects. It's most likely non-baryonic. It's most likely not made of protons and neutrons. And the reason for that is we have this model in the evolution of our universe called bariogenesis. And baryogenesis is adding in the story of particle physics to cosmology to predict the abundances of things that we see now, and it has done an excellent job. You can't turn around and say, oh, there's a whole bunch of baryons out there that we just can't see, because that will screw up the story of baryogenesis significantly. So the conclusion of that is that whatever this dark matter is, it is not simply protons or neutrons. Okay? It's most likely cold. If it was hot, it would actually smear things up. It can be axions, they can be sterile neutrinos, or they might be WIMPs, weakly interacting massive particles. Okay, there's several options that are still being explored. But that is essentially the story of dark matter. And now I want to turn to the alternate story of dark energy. Okay? Dark energy is essentially us trying to figure out, where the hell did this come from? Okay? So I hope you realize the term vacuum and the term energy are being interchanged here. This is stupid, but it's what's been done. Because this contributes to energy densities of the universe. These are all energy densities. But for whatever reason, we want to associate this with this. Okay? So we know that the energy density contribution to the current universe is about 0.7 from vacuums. And, you know, where this gets a little bit weird, you know, there's a whole bunch of models you can use to estimate this, estimating various quantum calculations that would give rise to vacuum energy contributions. But here's where it gets really weird. Where it gets really weird is that right now, this is kind of close to this. However, remember this. One of them scales as the scale factor cubed, 1 over that, one of them is constant. The fact that these are about the same now, you could go in anthropic principle, you could say that's why we're here. We get to look at it because these things are balancing, but it's not very scientifically satisfying. Okay? So this is the dark energy problem. It's trying to basically understand what this contribution is coming from, but moreover, why is it almost on par with the matter energy density? Okay? And there are various proposals for sorting that out. You can actually couple a scalar field to general relativity with a very relaxed potential so that the value of the potential is actually going to dictate this. And so this is adding something to general relativity. This is not doing something with general relativity by itself. But at any rate, if you add this field into general relativity, then this value is actually going to be, this is going to evolve by the evolution of this, and so it can relax itself to whatever it needs to in conjunction with the dynamics of that in order to achieve this balance. So I'm not going to go into any details about that, but that's a possibility. Okay? And I'm just kind of run through these quickly. There's a lot of them. We then have the cosmological constant problem. All right? And the cosmological constant. Well, the cosmological constant is essentially a statement about calculating this directly. It's not about the balance between it and the matter or anything like that. It's just about calculating this directly. It turns out that in our understanding of physics, through the whole process of bariogenesis and all of this stuff that we feel really comfortable with, we can calculate some contributions to this which we're relatively comfortable with. There might be some additional contributions from very early in the universe when everything was quantum gravity, dominated. But, over the late evolution of the universe, we can get some reasonable contributions to this. We can talk about the non-perturbative evolution of something where we start out at maybe here on the potential governing the system, and then over time, we start out early in the universe with a potential that looks like this, and then over time, that potential actually evolves to look like this, and after it evolves to look like this solution will eventually, under a perturbation, move down here, and then the difference in energy is released as vacuum energy. Anybody ever seen a diagram like this? This is the Higgs process in particle physics. But anyway, we know this happened, for sure. And this process of rolling from what was a stable equilibrium and becomes an unstable equilibrium and now rolling down to a stable equilibrium, releasing vacuum energy, we can calculate an estimate of what that would give to the vacuum energy of the universe. Also, we know that quantum field theory is very applicable. And when you do quantum field theory, what you basically do is you take space-time and you say, there's a field of the electron defined on it. And at each point, we can kind of treat it like a harmonic oscillator. So a field is just a continuum of harmonic oscillators at every point. Now, let me ask you a question. What's the ground state energy of a harmonic oscillator? Is it 0? Nope. What is it?
Is it 1/2 something?
Yeah, it's 1/2 h bar. Okay? So each of these is contributing 1/2 h bar, but there's a continuum of them for each type of particle. There are 27 of them in the standard model. That contributes a ton of energy. Now it turns out that that sum is a little bit naive. You got to be a little bit more sophisticated. And there is a way to be more sophisticated in this sum. It's called putting in a high energy cutoff, because this story can't hold back to infinite energies. There's got to be a cutoff. But anyway, even if you put that in, when you calculate the contributions to the vacuum energy density of the universe using all of this, what you'll get is 10 to the 108 electron volts to the 4th. Okay? This is the calculated, from quantum stories, value of the vacuum energy density of the universe. Now we know that V0 is 0.7. I've got it up here. So we can ask, what do I get if I convert this into electron volts to the 4th? Because obviously electron volts are going to involve the electron constant and all this shit. It's going to get really, really small. Here we go. You ready? 10 to the minus 12. Yes, folks, that's 120 orders of magnitude, distinguishing what is observed versus what we calculate. It's a bit embarrassing, isn't it? Yeah, it sucks. That's why many physicists call the cosmological constant problems one of the most embarrassing blunders. And it's got to be fixed. Because 120 orders of magnitude, it's just like, that's not a small approximation error. It's something way worse. Yes?
And it's at least consistently wrong, right?
Yes, very consistently wrong. Okay? But we're not done. We've got more to go. I hope you realize there's many open questions in cosmology. We're making progress, but we haven't solved one of these yet. Well, actually, we've solved one at the end. Then we have the baryon asymmetry of the universe. Again, we're focusing on baryons because the electrons, they are so small they don't really matter. What do you think the baryon asymmetry of the universe is due to observing? Yes?
Matter versus antimatter?
Yeah, this is essentially saying we have more matter than antimatter because you have baryons and antibaryons. How much antimatter is there in the universe? There's none. I mean, there's a little bit, but I mean, it's pretty much zero compared to the matter. Okay? So, this is one of my favorite things. Actually, when I took that cosmology course, I set up an entire website, because we had to do a project at the end. I had to do a whole website on the Baryon asymmetry of the universe. So I used to know a lot about it. I forgot it all. But anyway, here's the most amazing thing about that. In our observation of the universe, we have all matter and no antimatter. Is the Baryon asymmetry of the universe a problem of explaining why everything is matter and no antimatter? What do you think? Yes, no?
The way you're phrasing this, I would say no.
No. Here's the Baryon asymmetry of the universe problem. If we backtrack to early universe, you're going to have antibaryons. In fact, given the number of baryons we have now, if you go back to the earliest parts of the universe, one part in a billion. We'll have the same amount of matter as antimatter with the exception of 1 part per billion. If you think about it, holy shit, that's a very small difference. And that's why it's a pain in the ass. It would be very easy to explain why we have all matter and no antimatter. You could just write a law, a conservation law, and that would solve it. Or it would obviously be easy if we had exactly the same amount. Again, a conservation law would do it. But how in the hell do we get a 1 in a billion difference in the early stages of the universe? That is hella hard. Okay? Now it turns out that Sakharov back in the 60s came up with at least 3 key ingredients in order to explain this. He said, first and foremost, you have to have a process which creates baryons and not antibaryons. And what's important is in the standard model, that's our model of particle physics, baryon number is conserved. You can't create a baryon without creating an antibaryon. It's impossible. We have what's out there, but we can't create more baryons than antibaryons. So the first step you need is called a baryon number violating process. Okay? That is, you got to be able to do a process where you start out with a baryon number that's 10, and the baryon number changes to 11. So maybe you've introduced a single baryon but no extra antibaryons. Well, there's a problem with that. If that process is allowed, it will increase the number of baryons. An identical process is allowed which creates an antibaryon. Because of this symmetry in nature called CP, charge parity conservation. So I can have a process which increases the total number of baryons, but I must also have the process which also increases the total number of antibaryons. That's where we need step 2, which is CP violation. We need a process which, if you think about it one way, it's not equivalent in its rate to the other way. But that doesn't get it either. Because at the end of the day, the densities in this universe, it's a thermal system. You can have different rates, but in trying to achieve equilibrium, because the baryons and the antibaryons, they have the same energy densities, it will use the less dreadful route more rapidly than the more common route just to get equilibrium. So you have to have a violation of equilibrium. Okay? If you can find a process which satisfies all 3 of these criteria, then you're looking at a potential candidate for solving the baryon asymmetry of the universe. All right? And I'll guarantee you this is a problem which cannot be addressed just with general relativity. This is obviously a very particle physics heavy problem. So well, the cosmological constant is a problem which actually some people just use general relativity methods to address. Dark energy, dark matter, not so. Okay? Now I'm going to end the class with another 3 problems which were actually solved by something that you've heard of. So I'll go very quickly. It's not going to take long. Let me just give you the synopsis of the 3 problems and then what their solution is. First, we have the flatness problem. That is, omega equals 1 is an unstable fixed point under the growth of A. So if we consider omega equals 1 in this model of the universe, the Friedman equation, this solution is actually unstable. So how in God's name we got to omega equals 1 is weird. I mean, yes, we might magically be living at the point omega equals 1, but any fluctuation is going to knock us away from it. It's unstable. Okay? So this is called the flatness problem. Why in the hell is our universe flat? Because remember, this means k equals 0. All right? Then we have the horizon problem. If we look out at the cosmic microwave background, we will notice that what's over there looks the same as what's over there. However, given our understanding of the evolution of our universe, what is over there has never been in causal contact with what's over there. The light from over there could never have reached over there. Whatever's happening over there could not have influenced what's going on over there, so how the hell are they the same? Okay? Don't know. That's the horizon problem. And then last but not least is the relic problem. And the relic problem is essentially the absence of magnetic monopoles in our universe. We don't see magnetic monopoles. Okay? They should exist. Because it turns out, throughout the history of our universe, we have had these non-perturbative transitions. Symmetries have been broken. During the Higgs mechanism in particle physics, the symmetry of the universe was broken. Whenever you break the symmetry of the universe, including anything that has a U1 subgroup, sorry for getting technical, you will end up with domain walls, and at the presence of each domain wall, there will be a U1 instanton, which is basically a magnetic monopole. These should exist in the universe, and we don't see them. That's weird. Okay? Now, I said all 3 of these were solved. And they are. They are solved by the assumption, God, I have no idea what I put in there. Anyway, they are solved by an acceleration, oh, it's the number sign, which is proportional to the time, or the exponential of the time. This is called inflation. Okay? Note, this is what you would have if you were energy dominated by the vacuum, by the vacuum. Okay? But we can't even say we're dominated by the vacuum right now. Remember, these are solutions only if you're dominated by one of these and the rest of them are effectively 0. Okay? So what was proposed was if at some point in the past, the universe was undergoing an exponential expansion rate, which is called the inflationary period. It's basically going from a steady growth to it solves all 3 of these. It might not be obvious, but omega equals 1 is a stable point under an exponential growth. It might not be obvious, but you can have things which are causally connected, and then if there's an exponential growth and we don't know about it, that's the important thing, then when they appear to us, they're like, oh, they're not causally connected. Oh, they were. They're just not anymore. Okay? But if you put this into our history, then it says, oh, they were causally connected. And then last but not least, it dilutes the shit out of those monopoles. So too to the point where any measurement we make of 0 is held true. Okay? So Alan Guth proposed the inflationary model as a resolution to those 3 problems. It's been relatively well accepted, but there are a lot of details about that. We want to explain why this happens. So there's still a lot of open questions even in the inflationary models. That's it, folks. Thanks for yet another wonderful semester. I really, really do appreciate it. I wish to hell we could have looked at each other without our masks, but maybe next time. Okay?